In this code snippet, the essential libraries like NumPy, Pandas, Matplotlib, Seaborn, and Plotly Express are imported to carry out data analysis and visualization tasks proficiently in Python. Let's take a closer look at the role of each library. 1. NumPy is the go-to for numerical computations in Python, offering robust support for arrays, matrices, and mathematical functions to expedite numeric operations. 2. Pandas is a potent data manipulation tool built on NumPy. Pandas introduces data structures such as series and data frame, simplifying the handling and analysis of structured data. 3. Matplotlib. Known for its versatility, Matplotlib stands out as a favored plotting library capable of crafting static, animated, and interactive visualizations in Python. It boasts an array of plots, charts, and customization features. 4. Seaborn. Since serving as a Matplotlib-based data visualization asset, Seaborn offers a user-friendly interface for generating appealing and informative statistical graphics, streamlining the creation of intricate visualizations. 5. Plotly Express. Plotly Express emerges as a high-tier data visualization library that produces interactive plots with the help of Plotly's. It facilitates the creation of diverse plots with minimal coding, yielding interactive and web-compatible visuals. By incorporating these libraries, the code establishes an environment conducive to effective data handling, analysis, and the crafting of insightful visualizations for enhanced understanding and presentation of data. Each library fulfills a distinct function in data analysis and visualization endeavors, rendering them indispensable for any Python-based data science or data analysis initiatives. This snippet of code is designed to retrieve and organize stock market information on Google Stock from a CSV file corresponding to a particular time frame. It leverages the Pandas library for reading the CSV content and importing it into a data frame structure. By specifying date as the indexal and date as the parse dates, Pandas is instructed to designate the date column as the data frame index and interpret it as a datatime entity. Once executed, the Google head method showcases the initial rows of the data frame, offering a swift glimpse into the dataset's composition and contents. This initial scrutiny is crucial for gaining a preliminary understanding of the dataset before delving into subsequent analytical or visual tasks. Employing this code is pivotal for assimilating data from external origins, here exemplified by a CSV file housing Google's historical stock market details. Transforming this data into a Pandas data frame streamlines the procedures for dissecting, adjusting, and charting the data to facilitate further exploration and informed decision-making processes. Here's a snippet of Python code leveraging the Pandas module to import data from a CSV file named inst2006 into a data frame dubbed Microsoft. Setting the indexal parameter designates the date column as the data frame's index. Also, the parse dates parameter assists in converting the date column into datatime instances. Following the CSV file import, the code proceeds to exhibit the initial rows of the Microsoft data frame utilizing the head function. Utilizing this code snippet proves beneficial for tasks involving the scrutiny or manipulation of tabular data preserved in a CSV file. With Pandas functionality, it becomes convenient to extract data into a data frame, manipulate the dataset, carry out analyses, and visually represent the information. Incorporating the Pandas library in Python, this script is designed to fetch and analyze Amazon stock market data from January 1, 2006 till January 1, 2018, stored in a CSV file. The code assigns the date column as the data frame's index and interprets it as dates upon importation. This approach enables seamless manipulation and analysis of time series data. Employing the head function offers a sneak peek into the initial dataset entries, aiding in understanding its contents. This method is pivotal for efficiently loading and scrutinizing the historical stock market data. With the date column redefined as the index and converted into date formats, a host of time-related functionalities like filtering, grouping, and plotting the data across different time frames become accessible. This tailored arrangement streamlines the handling of time series data in Python through the Pandas library. This script imports data from a CSV file named im2006 into a Pandas data frame labeled im. By setting the indexal parameter to date, the script designates the date column as the index of the data frame. Moreover, the parseDates parameter is utilized to convert the date column entries into dataTime objects. Once the data is loaded into the data frame, the script uses the head method to exhibit the initial rows of the data frame. This piece of code serves the purpose of transferring a dataset into a pandas data frame for subsequent analysis and modification in the Python ecosystem. Leveraging pandas streamlines the handling and examination of extensive datasets by offering an array of functions and techniques to efficiently delve into and process data. The Google describe function seems to offer a means to access insights or specifics regarding Google's services, functionalities, or attributes. This function isn't your run-of-the-mill Python command, therefore its precise operations would hinge on the specific scenario it's employed within, such as a tailored function or method tied to a Google-oriented framework or software. Employing such a function could serve the purpose of acquiring insights on Google's CAPAs, services, resources, or any other pertinent particulars that aid developers in comprehending or engaging with Google's technology more proficiently. By detailing or furnishing metadata on Google's offerings, developers can leverage this data to seamlessly integrate Google services into their applications, troubleshoot challenges, or delve into the array of functionalities at their disposal. The code snippet Google columns doesn't align with standard Python syntax or libraries, so it lacks a specific function and might be a typo or incorrectly formatted. Nonetheless, in the realm of programming and data analysis, working with columns in a dataset is a fundamental task. Extracting insights, performing computations, and spotting trends often call for interacting with data stored in columns. Python programmers commonly turn to libraries like pandas for this purpose. Through the utilization of tools like pandas, we can import various types of dataset files, such as SPSS or Excel spreadsheets, into a data frame and subsequently access their columns by referring to the column names. This streamlined approach enables efficient data manipulation and analysis in a Google Colab setting, if the aim is to manage columns in a data frame or dataset. Leveraging the pandas library is a viable route to accomplish this task. It looks like you're attempting to retrieve information by using the info method on a variable labeled as Google. However, it's tough to offer precise guidance without the complete context of the code in question. In Python, the info method is not a typical built-in function. If it's a personalized method created within your codebase, its behavior would be specific to how it was coded. To give a thorough explanation of this code snippet, I'd require insights into the Google variable's definition and the specifics of how the info method is structured within it. Otherwise, providing a clear explanation would be challenging. In this code snippet, the ISNA method is used on a pandas data frame named Google to detect any missing values. The method generates a Boolean data frame reflecting missing values as true and non-missing values as false, maintaining the original shape. Following that, the sum method is utilized to tally the quantity of missing values in each column of the data frame along the vertical axis 0, resulting in a series object detailing the missing value count per column. Employing this code allows for a swift assessment of absent data in the Google data frame, a crucial step in data preparation and refinement to ensure data quality and consistency before proceeding with any subsequent analyses or machine learning tasks. Awareness of the quantity of missing values in each column empowers informed decisions regarding suitable handling or imputation of missing data. The function Microsoft described does not hold a universal significance in programming. It seems more like a made-up concept tailored to a specific situation or context. Typically, functions are named to reflect their intended operation, emphasizing the importance of choosing descriptive names. In a broader context, employing a described function or method might involve supplying details or metadata about an object, service, or data structure. This function could furnish a synopsis of properties or attributes of a given entity, aiding in comprehending and scrutinizing the object further. Practically, the describe method could serve various purposes such as data analysis, object examination, document creation, or any scenario necessitating information gathering about a particular entity. It furnishes a swift overview of the object, streamlining comprehension and usage. The command Microsoft info lacks a standardized interpretation in Python. Typically, functions such as info are not inherent to Python but are more likely tailored to specific libraries, modules, or customized classes in order to decipher the functionality of Microsoft. Info. Understanding the surrounding context is essential. Judging by the name, it appears to be a method designated within a unique class associated with Microsoft or an external library. When coming across this code in a particular program or library, consulting the specific software's documentation or source code is advisable to grasp the intent and operations of the info method in the Microsoft module or class. The code appears to be designed to detect any absent values within a dataset, possibly utilizing Microsoft's data handling toolkit. It seems to employ a function named isna to pinpoint missing values like none or none within the dataset, subsequently tallying them to determine the total count of missing entries. Ensuring the absence of missing values in a dataset is a pivotal phase in processing and refining data. Managing missing data holds significance as it can impact the precision and dependability of any analytical outcomes or models constructed with that data. By employing this code snippet, we can promptly identify the presence of missing values and take necessary measures, such as substituting values or eliminating incomplete data rows to uphold the integrity of our analyses and models. The function Amazon info appears to be a call to the info function associated with an object labeled Amazon. Typically, info could be a theoretical function aimed at offering insights about a specific object or entity. It likely serves to furnish particulars or metadata linked to an Amazon entity. In a more specialized programming scenario, understanding the functionality of the info method situated within the Amazon object is crucial to decipher the type of information it delivers. In practical terms, this kind of script would likely be integrated into a program developed in a programming language that utilizes objects and methods for efficient data organization. By invoking Amazon info, you would be seeking precise specifics or insights about the Amazon object, which could aid in tasks such as data display, decision-making based on information, or data manipulation. The function Amazon described is commonly found in a program or script written in programming languages like Python. It interacts with the Amazon Web Service using an Amazon key or API. This line of code likely invokes a method from the Amazon key or API to fetch detailed information or metadata regarding an Amazon resource. Be it a product, service, or account, this retrieved data could encompass various details like the resource's name, characteristics, specifications, or current status. By engaging with the Amazon service through such code, developers gain the capability to programmatically access and control Amazon resources. This opens avenues for task automation, system integration, and developing tailored applications that capitalize on Amazon platform features. Integrating snippets like this into a program provides developers with a swift and precise way to gather specific details about Amazon resources. Eliminating the necessity for manual input, this functionality proves valuable for activities such as data analysis, monitoring, reporting, or streamlining repetitive operations within an Amazon ecosystem. In particular programming languages like Python, Amazon columns typically denotes a method or attribute associated with a data structure, such as a data frame in popular libraries like Pandas. The purpose of this code is to likely fetch the column labels or names from a data frame labeled Amazon. When you invoke Amazon columns, you would obtain a collection or array containing the column name stored within the data frame. This feature proves handy in tasks related to data analysis and manipulation as it offers a swift way to visualize the data structure, access specific columns by name, and execute diverse operations on the columns housed within the data frame. This snippet of code comes in handy to identify any missing or not available values within a Pandas data frame named Amazon. Let me break it down for you initially. Amazon ISNA generates a data frame that mirrors the structure of Amazon, with each cell holding a Boolean value signaling the presence of a non-missing entry. Subsequently, Amazon ISNA sum tallies up the quantity of non values for every column in the data frame, aiding in the pinpointing of columns with absent data. By running this code, you promptly obtain an overview of missing values in the Amazon data frame, a key step in data tidying and preprocessing before delving into any analytical or modeling tasks. The detection and management of missing data prove pivotal in upholding the precision and dependability of your data analysis outcomes. The function IM describe is commonly seen in programming to call a method within a class object such as IM. This method, describe, typically offers a thorough summary or description of the IM object's details. In contexts like data analysis or machine learning, the described function proves handy in computing various statistics like count, mean, standard deviation, and minimum and maximum values for the dataset attributes linked to the AIM object. This helps users quickly grasp the data's distribution and fundamental characteristics. Implementing this code can be beneficial for comprehending the dataset, pinpointing outliers, assessing data ranges, and aiding in decisions regarding data preparation and model choices. Additionally, it assists in flagging data quality concerns or irregularities before advancing to subsequent analyses. The code snippet appears to be aimed at accessing the columns attribute of a pandas data frame. In pandas, the columns attribute denotes the labels of the columns within the data frame. By utilizing this attribute, the code likely aims to fetch the array of column labels contained in the data frame. Such information proves valuable for comprehending the data's arrangement within the data frame, enabling the extraction and alteration of particular columns, or conducting operations tied to these column labels. Grasping a data frame's columns holds significance as it facilitates data manipulation, analysis, visualization, and various other data entry functions. It empowers users to interact with and manage specific columns more efficiently and proficiently. This snippet of code scans through a data frame named IM to detect missing values and calculates the total count of missing values per column. Let's break down the functionality of each component of the code. 1. Data frame IM. This is the target data frame subjected to the missing value analysis. 2. Method ISNA. It is employed to identify missing values null or non within the data frame. The resulting data frame, retaining the original shape of ADAM, showcases Boolean values signifying the presence of missing elements. 3. Method sum. This function aggregates the Boolean results column-wise by transforming true indicating a missing value to 1 and false to 0. The method sums up these values for each column. This code snippet is instrumental in swiftly gauging the extent of missing data in each column of the data frame. This preliminary step is crucial during data refinement and preprocessing. Understanding the quantity of missing values in each column aids in determining suitable procedures for managing such gaps, whether through imputation techniques or discarding entries. The following script removes all rows with missing values not in or none from the data frame item and updates it directly without creating a new data frame. Dealing with missing values is crucial to ensure accurate analysis and modeling outcomes. By eliminating rows with missing values, we guarantee the cleanliness of our data, enabling precise analysis and modeling. The implant true argument alters the original data frame item itself, instead of producing a new data frame devoid of missing values. The following snippet of code serves the purpose of identifying any absent null or non values within a pandas data frame column or series. Let me break down its functionality. The code assumes item to represent either a pandas data frame or a series. Within pandas, ASNet is a function that produces a Boolean mask akin to the data frame shape. It labels missing values as true and present values as false. Subsequently, sum is invoked on this Boolean mask. It interprets true as 1 and false as 0, calculating the total count of missing values in the column or series. Employing this code enables a swift way to pinpoint the quantity of missing values in a specific column or series within a data frame. It's a handy tool for detecting the extent of missing data in a dataset, facilitating further scrutiny or decisions on how to appropriately manage these absent entries. The script creates a histogram utilizing Plotly Express, a Python library. It visualizes the distribution of the closed column within the Google data frame. Each bar in the histogram displays the frequency of closed values falling within a designated range. Including marginal box integrates a box plot into the histogram, offering insights into the data distribution. By setting bins 47, the histogram is divided into 47 bins. Defining Titlan distribution of close assigns a title to the plot. Furthermore, Fig update layout workup 0.1 minimizes the spacing between bars in the histogram. Conclusively, executing Fig showcases the histogram with the specified attributes. This code snippet effectively visualizes the distribution of closed prices in the Google data frame, simplifying the comprehension of data trends and variations. In this Python script, a histogram plot is crafted using the Plotly library to visualize data effectively. Here's a rundown of what it accomplishes. 1. By targeting the open column within the Google data frame, A histogram plot is formed. 2. To offer further insights into the distribution, a box plot is superimposed onto the histogram. 3. The histogram bars are distinguished by a striking red hue. 4. The title of the plot is designated as distribution of open. 5. The bar gap parameter is adjusted to 0, 1, controlling the gap width between histogram bars. 6. Finally, the plot is rendered using the show function. This code snippet proves invaluable for visually examining the distribution of open prices in the Google data frame, rendering data comprehension more accessible. The amalgamation of a histogram and box plot provides a holistic representation of the data distribution. Utilizing the Plotly Express library, the code below generates a scatter plot by employing the piece scatter function. It feeds the open and close columns from the designated data frame, Google, to the X and Y axis correspondingly. Each marker on the plot is set to an opacity of 0, 8, and the plot is labeled open versus close by including the line fig. Update to trace marker size of 5. The code regulates the marker size to 5 on the scatter plot. To showcase the plot, the final touch is the implementation of fig. Show. This script aids in illustrating the correlation between the opening and closing prices of a specific stock, possibly Google. It's a prevalent technique in financial analysis to graphically represent the connection between these prices, aiming to detect any valuable patterns or trends pivotal in investment decision-making. The function Google core isn't a standard feature in Python. However, if used in a pandas data frame where Google represents a column series, it likely calculates correlations between the Google column and all other columns in the data frame. In pandas, the core method is handy for computing correlations between data frame columns. By default, it computes the Pearson correlation coefficient, which gauges the linear association between two variables. The coefficient values range from 1 to 1, with 1 suggesting a perfect positive linear relationship, 1 a perfect negative linear relationship, and 0 indicating no linear relationship. This type of examination aids in unraveling the connections between different variables in a dataset. It proves valuable in data exploration, pattern recognition, and decision-making based on the insights derived from correlation analysis. Utilizing Python's pandas library, this code snippet generates a plot showcasing Google's stock attributes within a defined timeframe spanning from 2008 to 2018. The process unfolds as follows. 1. By utilizing Google 2008-2018, the code extracts data related to Google's stock attributes from the years 2008 to 2018. 2. Subsequently, calling plots of plots true, fixes 12 enables the visualization of the retrieved data as subplots with a specified figure size. 3. The line plot title Google stock attributes from 2008 to 2018 assigns a title to the plot. 4. Finally, executing plot show presents the plot to the user. This code proves valuable for illustrating the evolution of Google's stock attributes throughout a designated period. By unveiling trends, patterns, and fluctuations in stock prices, such visual representations empower analysts and stakeholders to craft well-informed investment strategies. The provided code snippet displays a visual representation of the Microsoft stock characteristics spanning from 2008 to 2018. It leverages the pandas library to extract data for this specific time frame, subsequently employing the plot function to generate individual subplots for each stock attribute. The sizing of the plot is determined by the fig size parameter. The primary objective of this code is to illustrate the fluctuations in various Microsoft stock attributes across the designated years. By graphically presenting this information, trends and patterns within the stock data become readily observable and open to analysis. Such visualization proves beneficial for investors, analysts, or anyone keen on comprehending the historical evolution of Microsoft stock during the specified time frame. This piece of code utilizes pandas and matplotlib libraries to showcase various characteristics of Amazon stock data spanning from 2008 to 2018 through multiple subplots. The segment Amazon 2008-2018 is presumably filtering out the stock data for the indicated time frame. By specifying plots of plus true, fixes 12 distinct subplots are generated for each attribute under scrutiny, such as open, close, high, and low prices. The fixes 12 parameter is used to determine the dimensions of the figure presenting the subplots. Upon plotting the data, plot Titly stock attributes from 2008 to 2018 is employed to assign a title to the plot. Conclusively put, show is called to exhibit the plot on the screen. This code proves to be valuable in visually capturing the trends and patterns within Amazon stock attributes throughout the designated period, aiding in a deeper analytical understanding of the data. Such visual aids can play a crucial role in facilitating well-informed decisions regarding stock trading actions or investment strategies. Utilizing the plot function, this script showcases multiple subplots portraying diverse stock characteristics of the item stock from 2008 to 2018. Setting subplots true enables the creation of distinct plots for each attribute, while the fixes 12 parameter establishes the dimensions of the encompassing figure housing these subplots. Through the use of pult title, the script assigns a title to the entire plot, signifying its focus on displaying item stock attributes across the specified time frame. Constructing subplots for individual attributes proves beneficial in visually analyzing time series data, facilitating the comparison of different facets of stock performance. This method allows for the observation of the evolution of item stock attributes throughout the designated period, aiding in the detection of any discernible patterns or correlations among them. Furthermore, incorporating titles and appropriately sizing the plot enhances its readability and overall visual appeal. The provided script generates line graphs illustrating the peak stock values of Google, Microsoft, Amazon, and item. Each line on the graph represents the highest stock prices of the respective companies throughout a specific time frame. To craft the visual representation, the plot function is leveraged to plot the lines, while the legend function is employed to incorporate a key on the graph denoting the individual companies. Ultimately, the show function is executed to exhibit the finalized graph. This code proves beneficial for visual assessments and juxtapositions of the peak stock prices among various companies across time spans. It aids in dissecting trends, identifying patterns, and evaluating the fluctuation in stock prices, all of which are pivotal in steering well-informed investment choices. The snippet of code carries out several key operations. 1. It normalizes the stock prices of Google, Microsoft, Amazon, and M by dividing each company's daily high price by the initial high price of that company's stock, then multiplying the result by 100. 2. It then generates a graph displaying the normalized stock prices of each company together, enabling a comparative analysis of their performances over time. 3. A legend is added to the plot to differentiate between the lines representing the various companies. 4. The final plot showcasing the normalized stock prices for Google, Microsoft, Amazon, and M is presented. This method of normalizing stock prices enhances the visual assessment of how different stocks have fared over time, aligning all prices to a common starting point. This approach proves valuable in scrutinizing and grasping the relative growth or decline of diverse stocks, especially when evaluating them collectively in a single plot. This script computes the expanding mean and expanding standard deviation of the high column within a dataset labeled Microsoft. It proceeds to generate a graphical representation showcasing the high column in correlation with the expanding mean and expanding standard deviation. The expanding mean gets calculated at each instance by averaging all values right from the initiation of the dataset up to that specific point. Likewise, the expanding standard deviation at each juncture derives from computing the standard deviation across all the values from the start to that particular point. Utilizing this script allows for a visual depiction of how the high values within the dataset evolve over time concerning the expanding mean and standard deviation. It can offer valuable insights into both the trend and volatility of the information. The inclusion of a legend, title, and visually appealing display is crucial to ensuring the graph is both informative and readily comprehensible to users. This piece of code is designed to compute and present the expanding mean and standard deviation of the high column within the Google data frame. Here's a breakdown of what each step accomplishes. 1. The expanding mean for the high column in the Google data frame is computed by using Google high expanding mean. 2. To determine the expanding standard deviation of the high column in the Google data frame, the code employs Google high expanding st. 3. Visualization of the high column from the Google data frame is created with Google high plot. 4. The expanding mean is visualized using Google mean plot. 5. The expanding standard deviation is visualized via Googlist plot. 6. A labeled legend showing high, expanding mean, and expanding standard deviation lines is included in the plot. 7. The plot is given the title Google. 8. Finally, the plot is displayed for examination. This code snippet proves to be valuable for visually examining the patterns and variability in the high column values within the Google data frame across time. Incorporating the expanding mean and standard deviation, such a visualization aids in recognizing trends, patterns, and potential outliers present in the dataset. In this code snippet, the expanding mean and standard deviation for the high column in the item dataset are computed. The expanding mean represents the average of all values up to a specific moment, while the expanding standard deviation is the deviation of all values up to that moment. Subsequently, the code visualizes the high column alongside the expanding mean and standard deviation on a matplotlib graph. A legend is included to distinguish the lines, and a title is added to the plot. This script proves valuable for tracking the data trends and fluctuations over time, aiding in the detection of patterns, anomalies, and gaining insight into the overall trend of high values within the item dataset. This script is designed to compute and display the moving average and rolling standard deviation of the high column within a data frame referred to as Amazon. By employing the expanding function, the code gradually increases the window size for the rolling computations, starting from the initial data point up to the current one. The mean and st functions then calculate the mean and standard deviation, respectively, of the expanding window specifically for the high column in the Amazon data frame. Following these calculations, the script proceeds to generate a visualization using matplotlib. It overlays the original high column data with the computed expanding mean and standard deviation values on a single graph. This visual aid is valuable for grasping the trends and variations present in the high column data as time progresses. The utility of this code lies in its capacity to assist analysts and data scientists in pinpointing patterns, trends, and peculiarities within the dataset across time. It furnishes a graphical representation illustrating the fluctuations in high column values concerning their long-term average mean and spread standard deviation. This script is designed to compute the expanding mean and standard deviation of the closing prices of Google stock. The expanding mean method computes the average of all values encountered up to a certain point in time, while the expanding standard deviation calculates the spread of all observed values up to that time. Following the computation, the script creates a visual representation displaying 3 lines, one representing the closing prices of Google stock, another portraying the expanding mean, and the last one showing the expanding standard deviation. This display aids in comprehending how Google's stock closing prices relate to their expanding mean and standard deviation as time progresses. Employing this script is vital in financial analysis for spotting trends, patterns, and anomalies in stock prices. It facilitates informed decision-making regarding whether to buy, sell, or retain the stock by leveraging statistical metrics such as mean and standard deviation. The provided code snippet imports essential libraries for adjusting plot size with reparams from PyLab and conducting statistical analysis with the statsmodules library in Python. PyLab facilitates interactions with matplotlib and configures plot settings utilizing reparams. Statsmodel serves the purpose of estimating and decoding statistical models. Leveraging reparams enables tailoring the appearance of plots, including figure dimensions, text size, color themes, among other aspects. Statsmodels offers a diverse array of statistical models and assessments not found in alternative libraries such as scikit-learn. It proves particularly valuable for intricate statistical examinations, econometrics, time series scrutiny, and the assessment of machine learning models. By including these libraries, the code prepares us for engaging in statistical analysis and personalizing plots to effectively visualize outcomes. The following code snippet serves to dissect the seasonal breakdown of Google's stock price data. Here's a breakdown of its functions. 1. By setting reparam's figure, fix size to 11. 9. The default size of matplotlib graphs is determined. 2. Decompose to Google volume sum. Seasonal decompose Google high. For 360 dissects Google's stock price time series, focusing on the high value, assuming a yearly seasonality with 360 trading days. 3. Running figure decompose to Google volume. Plot generates the visual representations of the decomposed data, showing observed trend, seasonal, and residual components. 4. To display the plot for visualization, plt show is employed. Utilizing such code is crucial for time series scrutiny, unveiling trends, seasonal variations, and irregularities in the dataset, offering valuable insights for forecasting and deciphering underlying data patterns. This type of analysis holds significance across diverse sectors like finance, economics, and various industries reliant on time series data. Here is a code snippet that breaks down Microsoft's stock price time series data for the high column. It employs the seasonal decompose function from the stats modules, some module to dissect the data into its fundamental elements: trend, seasonality, and residual components. To kick things off, the snippet adjusts the plot size to 11:9 dimensions by tweaking Recurrent figure, fig size 11:9. Following this, it dissects the Microsoft stock price data using the seasonal decompose function with a yearly frequency of 360, indicating an annual seasonality trend in the data. Subsequently, the code produces a visualization showcasing the decomposed constituents using matplotlib. To exhibit the plot, the pult show method comes into play. This piece of code proves beneficial in unraveling the underlying trends ingrained within a time series dataset, unveiling insights into patterns like trends and seasonal variations. Such revelations can be instrumental in forming well-informed decisions regarding forecasting and analysis. The following script configures the figure's display size, breaks down IM's high stock prices time series data into trend, seasonal, and residual components using a seasonal decomposition function, and illustrates the outcome of this decomposition. To specify the figure's dimensions for the plot display, the line reparams figure, fig size 11:9 ensures the figure appears with a width of 11 units and a height of 9 units. By calling some seasonal decomposition high for 360, the time series data for M's high stock prices undergoes decomposition. The function dissects the initial time series into trend, seasonal, and residual elements. With front 360, the function identifies the frequency for the seasonal decomposition, assuming a yearly seasonality pattern with 360 data points. Subsequently, the decomposed data is visualized through decomposed volume, plot, and presented using pult show. This code serves to scrutinize inherent trends and variations within a time series dataset, aiding in trend detection, seasonality recognition, and facilitating future data point analysis and forecasting. Below is a code snippet that breaks down Amazon stock high prices time series data into its key components: trend, seasonal patterns, and residual fluctuations. To ensure the plots are presented appropriately, the line reparams figure, fig size 11:9 establishes the default size for the figures. The next step involves utilizing the seasonal decomposition feature from the stats modules library with the line decomposed Amazon volume sum. Seasonal decomposition high for 360 by specifying a frequency of 360 yearly frequency. Assuming 360 data points in a year, the function dissects the time series data accordingly. The information within the time series is then segregated into 3 distinct elements: trend, seasonal fluctuations, and residual variations. The trend showcases the core pattern within the data, while the seasonal aspect captures recurring changes, and the residual element pinpoints random deviations post removing the trend and seasonality components. To visualize this breakdown effectively, the line figure decomposed Amazon volume plot generates a graphical representation of the dissected time series components. Finally, pult show is used to display the plot exhibiting the decomposed elements. By leveraging this code, valuable insights can be gleaned concerning the foundational tendencies and periodic variations of Amazon's high stock prices. These insights can be pivotal for informed decision-making and predictive analysis based on the segmented components. Here's a segment of a Python script designed to illustrate the breakdown of a time series dataset representing the closing prices of Google stock. The code performs the following tasks: 1. Adjusts the size of the figure to 11:9 using reparams. 2. Utilizes the seasonal decomposition function from the stats modules library sent to deconstruct the time series data Google stock prices into trend, seasonal, and residual elements. 3. Specifies a FIR value of 360, indicating consideration of an annual seasonal pattern. This choice means the function aims to capture seasonality repeating every 360 data points, likely denoting trading days in a year. 4. Subsequent to the decomposition process, the code generates a visual representation displaying the original data alongside the trend, seasonal and residual components. 5. Lastly, the plot show function showcases the plot on the screen for observation. This code proves valuable for time series analysis by unveiling the underlying data patterns and structures. By breaking down the time series into trend, seasonal, and residual segments, analysts can pinpoint diverse factors impacting the data like long-term trends, seasonal cycles, and irregular fluctuations. Such visualizations offer insights into data behavior, aiding in informed decision-making for forecasting and analysis purposes. The snippet of code provided adjusts the figure size for the plot through Matplotlib's params. Following this adjustment, the code utilizes the seasonal decompose function from the stats models library to break down the time series data of Microsoft's closing stock prices into fundamental components: trend, seasonality, and residuals. A frequency of 360 is denoted to signify a yearly seasonality trend within the data. After the decomposition process, the code proceeds to visualize the broken down components using the plot method and exhibits the figure via plot show from Matplotlib. Employing this code enables us to visually inspect and scrutinize the trend, seasonality, and residuals within the time series data. This visual analysis serves to unearth underlying patterns and fluctuations within the dataset over time. By decomposing the data, we gain insights into the prevailing trends and capture any cyclic variations present in the dataset. The following snippet of code establishes the plot's figure size, breaks down Amazon's closing stock prices data into trend, seasonal, and residual elements using a seasonal decomposition technique, and proceeds to visualize these decomposed components. To begin, the command reparams figure, figsize 11:9 determines the dimensions of the figure where the plot will be exhibited. Subsequently, the instruction decomposed Amazon volume sum, seasonal decompose Amazon close, fret 360 decomposes the time series data of Amazon's closing prices denoted as Amazon close into trend, seasonal, and residual constituents employing a seasonal decomposition algorithm. The specified frequency value fret 360 implies that the dataset is monthly, considering 360 days as a year. Lastly, the decomposed elements are showcased through decomposed Amazon volume plot and viewed on the screen by invoking plot show. This code snippet serves the purpose of scrutinizing the inherent patterns within time series data to glean insights about trends, seasonality, and irregularities present. By visualizing these aspects, one can facilitate data-driven decisions concerning forecasting, anomaly detection, and overall time series evaluations. This snippet of code tweaks the figure size by defining its width and height dimensions, and then proceeds to conduct seasonal decomposition on Amazon's closing stock prices time series data. This decomposition breaks down the series into trend, seasonal, and residual segments. The frequency parameter is configured at 360 to reflect an annual pattern within the dataset. Upon completion, the code generates a visualization of the decomposed elements and showcases it. Modifying the figure size comes in handy when aiming to manage the plot's proportions for enhanced readability and visual appeal. Seasonal decomposition serves as a valuable tool for scrutinizing and grasping the underlying trends and fluctuations within time series data, which proves vital for subsequent analysis and predictive modeling endeavors. The provided code excerpt parses a CSV file housing historical stock values for a specific company, Amazon in this instance. Initially, it imports the data into a data frame employing the readsv function from pandas. Subsequently, the data within the data frame is rearranged based on the date column via the sortValues method. Sequencing data by date proves pivotal in time series analysis, ensuring chronological order facilitating analysis or visualization. Lastly, by executing decomposition head, the code showcases the initial rows of the arranged data frame, granting a swift overview of the dataset. To summarize, this code snippet plays a crucial role in loading, structuring, and assessing time series data related to Amazon stock prices, laying the groundwork for further analysis or processing endeavors. Utilizing the Matplotlib and Seaborn libraries, this script generates a line chart showcasing the closing stock values of Amazon. To craft this visual representation effectively, 1. Embracing a dark grid style via scenes. Set style dark grid injects a sophisticated feel highlighted by grid lines. 2. Setting up a figure of 15.9 inches with plot Figure fix size in 15.9 lays the groundwork for the subsequent plot. 3. The line plot. Plot.Amazon executes the plotting of Amazon's closing prices extracted from the closed column in the data.Amazon data frame. 4. Tailoring the axis ticks with plot. Sticks ensures a refined presentation, displaying every 500th data point with rotated labels for enhanced readability. 5. With PILT, title, PILT, clibel, and PILT, tilabel, pertinent details like title, x-axis descriptor, and y-axis notation are seamlessly incorporated to enrich the plot's interpretative value. 6. Concluding with PILT, show elegantly renders the plot, offering a visual insight into the trajectory of Amazon stock prices. Employing this script crafts a vivid and insightful display of Amazon stock trends. Fine-tuning styles, including labels, and optimizing format choices collectively enhance the chart for a comprehensive analysis of the stock data. The following script parses a CSV file that contains stock market information for Alphabet Inc., formerly known as Google, from the designated file Google 2006 1 Connecto 2018 1 so it then arranges the data based on the date column in ascending order. Lastly, it exhibits the initial rows of the organized data using the head method. Employing this script is crucial for loading and structuring the stock market data to facilitate analysis, simplifying the exploration and extraction of insights from the dataset. Arranging the data by date guarantees that the data is in a chronological sequence, a customary practice when dealing with time-related datasets such as stock market information. The following script leverages the matplotlib library to present a line plot that visualizes the historical stock price behavior of Google. 1. Initial step involves importing essential libraries like matplotlib and seasonality, pivotal for crafting engaging data visualizations. 2. Style settings for seasonality plots are customized to dark grid specifically for this display. 3. A figure is established with a distinct size of 15:9 through PILT. Figure fig size in 15:9. 4. The plot showcases the closed price data extracted from a pandas data frame labeled Google using PILT. Plot Google glows. 5. To enhance clarity, ticks are positioned at every 500th index of the data, aligning with corresponding dates via PILT. Sticks. 6. For better legibility, the x-axis labels are rotated by 45 degrees. 7. The plot's title is designated as Google stock price, featuring a font size of 18 and bold font weight with PILT. Title. 8. Axes are clearly labeled date for the x-axis and closed price cust for the y-axis, both using a font size of 18 employing PILT, clibel, and PILT. Ilabel. 9. Lastly, the finalized plot is exhibited through PILT show. This code excerpt plays a critical role in data visualization, offering a comprehensive overview of Google's stock price trends across various time points. By harnessing the capabilities of matplotlib and seasonality, the script effectively crafts an informative and visually enticing line plot for a detailed representation of stock price data. This snippet of code is designed to import information on AIM stocks from a CSV file spanning from January 1, 2006 to January 1, 2018 into a pandas data frame. It proceeds to arrange this dataset by the date column in an ascending manner. It then showcases the initial few rows of the ordered data frame by leveraging the head function to confirm the correct loading and sorting of the data. Employing this code is significant as it streamlines the process of managing and modifying extensive datasets housed in CSV files through pandas, a robust library for data manipulation in Python. Sorting the data based on dates ensures a chronological organization, a vital aspect when assessing time series data such as stock values. In the context of a data frame named datatim, the following code snippet effectively eliminates any missing non-values directly within the original data frame rather than generating a fresh one. The absence of data can significantly hamper the process of data analysis and the effectiveness of machine learning models. Hence, this operation guarantees that the dataset utilized for analysis is more thorough and precise. The purpose of this code snippet is to generate a line plot illustrating the closing stock price trend of item over a period using Python's matplotlib and seasonality libraries. Here's a breakdown of what the code accomplishes to enhance visual appeal. The code configures the plot style to dark grid via seasonality. It initiates a plot figure sized at 15:9 inches. The code plots the closing stock price data sorted from the closed column within the datadim data frame. At intervals of every 500 data points, The axis ticks are positioned and annotated with corresponding dates from the date column. For ease of readability, the key tick labels are rotated by an angle of 45 degrees. The plot is titled IM Stock Price, presented with a font size of 18 in bold format. Both the axis and y-axis are labeled as date and close price cost, respectively, with a font size of 18 each. Lastly, the plot is displayed using Pult. Show. This code proves valuable for observing the historical trajectory of IM stock prices, aiding in recognizing fluctuations, trends, and potential patterns. Leveraging this visualization method can support decision-making processes concerning IM stock investments or trading activities. Part of a Python script, this code handles Microsoft stock market data from January 1, 2006 to January 1, 2018 stored in a CD file. Initially, the code imports the data into a pandas data frame and organizes it by the date column in increasing order. Subsequently, it displays the initial rows of the organized data frame using the head method. Analysis of historical stock market data benefits from this code. By loading data from a file, we gain structured access for manipulation using pandas. Sorting data chronologically aids in accurately tracking stock price fluctuations over time. Following that, utilizing the head method promptly examines the earliest data entries to validate proper reading and sorting executions. This piece of code leverages Python's matplotlib and seasonality libraries to craft a line plot illustrating the progression of Microsoft's closing stock prices across time. Here's a breakdown of the features. 1. By invoking a seasonality set style dark grid, the plot adopts a stylish dark grid backdrop facilitated by seasonality. 2. Pult. Figure fixes in 15:9 adjusts the plot's dimensions to 15 inches wide and 9 inches tall. 3. The line Pult. Plotted Microsoft close plots the closing price record sorted from the close column within the data Microsoft data frame. 4. Using Pult. Sticks range 0, data Microsoft, sheep 0, 500, data Microsoft date. GLA 500, rotation 45. The axis is marked every 500 data points while exhibiting corresponding dates from the date column with a 45-degree rotation for enhanced readability. 5. Bold. Title Microsoft stock price. Font size E18. Font weight bold assigns the plot the title Microsoft stock price along with a specific font size and weight. 6. The axis is denoted as date with a defined font size VH bold. Clipable date. Font size E18. 7. Similarly, the y-axis is labeled as close price cost with a specific font size using Bold. Belows price cost. Font size E18. 8. To showcase the plot, execute Bold. Show. Through this code, the trends in Microsoft stock prices throughout time can be visually depicted, enabling easier data interpretation for analytical or decision-making purposes. The flexibility offered by matplotlib and seasonality libraries allows for the creation of visually captivating and informative plots. In this piece of code, the close prices of Amazon stocks were fetched from the Amazon data frame and stored in a fresh variable named preAmazon. By invoking the info method on preAmazon, valuable insights about the data frame were unveiled, such as the count of non-null entries and the data types of each column. This aids in grasping the data structure and pinpointing any absent values or necessary data type adjustments. Employing info proves crucial for delving into the data and priming it for analysis, as it presents a swift snapshot of the data, enabling savvy decisions regarding managing missing data, data type conversions, or spotting potential dataset hitches. Utilizing the min-max seller class from the scikit-learn library, the script normalizes the close prices of Amazon stock. Min-max seller operates by adjusting the data to a specific range, typically between 1 and 1. This standardization is crucial in machine learning to ensure consistent scaling across all features. Such uniformity aids in enhancing the performance and convergence of various machine learning algorithms. The initial step involves setting up the min-max seller object with the desired range for features. Subsequently, the code applies the fit-transform function to the close prices of Amazon stock, reshaping the data to a single feature reshape 1:1 format as expected by the seller. Implementing this code guarantees that the close prices adhere to a standardized scale within the defined range, simplifying the process for machine learning algorithms to effectively handle this dataset. In its essence, the split data function processes time series stock data alongside a lookback parameter as key inputs. It transforms the stock data into a NumPy array and then divides this data into training and testing sets, setting the stage for a machine learning model to come into play. The mechanics of the function were as follows. Firstly, the stock data undergoes conversion into a NumPy array. Next up, an empty list named data is brought to life. Moving along, the function navigates through the array of stock data based on the lookback period, assembling segments of data into the data list. Post this data compilation, the data list transforms into a NumPy array. The function then maps out the test set size, designated as 20 of the data length, leaving the remaining as the training set capacity. For the training phase, the feature set train is crafted by extracting all rows leading up to the training set capacity, while discarding the last column. Meanwhile, the training labels train are shaped by fetching all rows until the training set capacity, focusing solely on the last column. When it comes to testing, the feature set test emerges by encompassing all rows starting from the training set capacity and omits the final column. In parallel, the testing labels test are born by encompassing rows from the training set capacity onwards, spotlighting only the final column. In the grand finale, the function delivers the training and testing datasets train, test, test neatly encapsulated within a list structure. This code snippet proves handy when fine-tuning time series data for a machine learning model hungry for historical data within a particular lookback framework. By segmenting the data into features and labels, the function lays out the groundwork for training and evaluating the machine learning model effectively. The presented snippet of code serves the purpose of dividing a designated dataset into input and output sequences for the training and testing phases of a machine learning model. The dataset in question appears to pertain to the stock prices of Amazon. The variable lookback dictates the length of the input sequences. The split data function is employed to generate the necessary training and testing data. Within this function, the original dataset is split into two sets: input sequences train, test, and output sequences train, test, in accordance with the specified lookback value. The output lines present the dimensions of the training and testing sets, offering insights into the sizes of the data arrays slated for use in training and evaluating the model. This code snippet assumes significance in the realm of machine learning for its role in data preparation. It ensures the proper structuring of input and output sequences, a critical prerequisite for enabling the model to assimilate data effectively and furnish precise predictions. The script below transforms NumPy arrays train, test, train, and test into PTorch tensor entities. PTorch, a well-known open-source machine learning framework primarily used for constructing and training neural networks, is the perfect tool for the job. When we switch the data to PTorch tensors, it enables us to leverage the computational graph and automatic differentiation features that PTorch offers. This simplifies tasks such as neural network training, gradient computations, and efficient model parameter adjustments. The conversion from NumPy arrays to PTorch tensor objects enables smooth integration of the data into our PTorch model. This adaptability streamlines tasks like training, assessment, and predictive analysis within the PTorch environment. The data transformation ensures seamless compatibility with PyTorch's tensor-centric operations and functionalities. The given code snippet is responsible for setting up initial values for various variables essential for constructing a neural network model. Let's delve into the significance of each variable in PutDim. This variable denotes the expected number of input features or dimensions that the neural network will work with. Hidden dim, it stands for the quantity of units present in each hidden layer of the neural network. Num layers, it determines the total count of hidden layers incorporated in the neural network structure. Cal PutDim, this variable showcases the number of output units or dimensions that the neural network will generate. NumPy, it reveals the total number of training epochs or iterations that the neural network will undergo during the training phase. These variables play a crucial role in establishing both the architecture and training parameters of the neural network model. The values assigned to these variables are pivotal in shaping the neural network structure and behavior throughout the training procedure. They directly impact the model's performance and its effectiveness in learning from the provided data. This script presents a custom implementation of a GRUI-gated recurrent unit neural network module in PTorch. GRUI is a variant of recurrent neural network commonly employed in tasks like time series forecasting and natural language processing. Within the decomposition function, the class sets up the GRUI network by specifying input dimensions, hidden layer sizes, layer count, and output dimensions. It instantiates the GRUI layer using nin. GRUI and a linear layer using nin, linear, in the forward function. The input sequence X undergoes processing through the GRUI layer to produce the output. The initial hidden state 0 is initialized as a tensor filled with zeros, based on the specified number of layers and batch size. Subsequently, the GRUI layer's output is fed into the linear layer to yield the final result. This code is vital for tailoring a personalized GRUI model structure designed for a specific task. It enables us to set the input-output dimensions, hidden layer dimensions, and layer quantities. Crafting our own GRUI module grants us the liberty to adapt the neural network's architecture to best fit the demands of the problem at hand. Ultimately, this script lays out the framework required for training and utilizing a GRUI model within a PTorch framework. The provided code excerpt establishes a GRUI-gated recurrent unit model utilizing PTorch, a popular library for deep learning. Here's a breakdown of each segment within the code. 1. Function GRUI input dim, hidden dim, output dim. Num layers initiates a GRUI model with designated specifications for input dimension, hidden dimension, output dimension, and the number of layers. 2. The instantiation of torch. Class reduction mean creates a mean squared error means loss function that computes the mean squared disparity between predicted and target values. 3. By initializing torch, coptim, adamodel, parameters, residual. 1. An atom optimizer is configured to adjust the GRUI model's parameters during training. The learning rate lower is set at 0, 1, which determines the optimization step size. This code is pivotal for outlining the GRUI model's structure, defining the evaluation criteria through the loss function, and establishing an optimizer to iteratively update the model's parameters utilizing computed gradients. These components are fundamental for effectively training a neural network model and optimizing it to generate precise predictions on the provided dataset. The provided code snippet is a fundamental segment of a training routine for a neural network model utilizing the PTorch framework. Here's a breakdown of its functionality to kick things off. An array called gist is initialized to preserve the loss history throughout training, and the starting point in time is recorded to gauge the training duration accurately. Moving on, the snippet iterates through a predetermined number of epochs numbipos. Within each epoch, it generates predictions utrainpred based on the model's evaluation of the training data train. The code then computes the loss between the forecasted values utrainpred and the actual target values utrain-GRUI by leveraging a designated criterion, such as mean squared error loss. Subsequently, the loss value for the ongoing epoch is displayed and saved within the gist array. By invoking loss backward, the gradients of the model's parameters are computed concerning the loss through backpropagation. To ensure a clean slate for each iteration, the optimizer's gradients are reset to 0 using optimizer. 0grad, the model's parameters receive an update by executing optimizer step, which adjusts them based on the computed gradients. Upon the conclusion of the training loop, the overall training duration is determined by subtracting the starting time from the current time. This code snippet assumes significance in the process of training neural network models, as it executes pivotal training procedures like forward propagation, loss computation, backpropagation, and iterative parameter updates across multiple epochs. This iterative nature aids in the model's progression towards minimizing the loss function and enhancing performance on the assigned task. In this code snippet, the process involves reverting predicted and original values from a tensor format, detached from the computational graph, to their initial scale utilizing a scalar. Here's an overview of the code's function. 1. Initially, it acquires the model predictions utrainpred and true values utrain-GRUI from tensors. 2. The code makes use of the scalar inverse transform method to undo the scaling effect that was initially applied to these values during preprocessing. This step is crucial since the neural network might have been trained on scaled data to enhance the training phase. 3. By employing detach numpy, these tensors were transformed into numpy arrays devoid of gradient tracking, allowing for operations like inverse scaling. 4. Subsequently, these numpy arrays are converted into pandas data frames named predict and original to facilitate data manipulation and visualization. It is a standard procedure to scale input data during neural network training to ensure steady convergence and improved performance. Following the training and prediction stages, it is vital to reverse the transformation of both forecasted and real values to their original scales to interpret and assess the outcomes effectively. The provided script utilizes the Seaborn library to craft a visual representation. Initially, the code establishes the plot style as darkgrid through sins. Set style darkgrid. Next, it generates a figure by invoking pult figure and fine-tunes the spacing between subplots with fig. Subplots adjusts by 0, 2, space 0, 2. Following this, it plots a line chart on the primary subplot 1, 2, 1 to exhibit both the original data and predictions. Subsequently, it assigns a title, X and Y-axis labels, and tweaks the visual aspects of the plot. Within the secondary subplot 1, 2, 2, a separate line plot is fashioned to showcase the training loss history, with its appearance customized accordingly. To conclude, it specifies the dimensions of the figure. This code proves valuable for crafting visually compelling visualizations for data scrutiny, dataset comparison, and monitoring training evolution, all of which offer substantial benefits in realms like data analysis, machine learning, and other diverse fields. The algorithm in question computes the root mean squared error by contrasting the actual values contained in utrain and utest against the predicted values utrainpred and utestpred. This comparison is based on the application of the mean squared error function found within the sklearn metrics module. RUMS plays a crucial role in assessing the disparities between predicted values from a model or an estimator and the actual observed values. Here's a breakdown of the process. The model's predictions utrainpred and utestpred undergo a reversion to their initial scale through the utilization of Saylor inverse transform method. The original scaling of the ground truth values utrain and utest is also reinstated. Subsequently, RUMS is computed for the training and testing datasets using the mean squared error function, followed by taking the square root with the aid of math. Set. The resultant RUMS scores for both the training and testing sets are then showcased on the console. Conclusively, the training and testing RUMS scores together with the training time are included in the GRUI list. It's assumed that GRUI has been previously initialized as a list within the codebase. Evaluating the efficacy of regression models hinges significantly on RUMS since it furnishes a lucid assessment of the model's precision in predicting numerical outcomes. Lower RUMS values synonymize with heightened performance levels of the model. In cases involving scaled data, the inverse transform phase is fundamental for reverting the values back to their native scale, thereby facilitating a clearer interpretation of the outcomes. The following script is designed to facilitate the preparation of data for plotting both the actual and forecasted price values. Let's break down the functionality of each segment. 1. 2 arrays. Train predict plot and test predict plot, or instantiated with non-values mirroring the shape of the pre-Amazon array. These arrays will serve as containers for the predicted values pertaining to the training and testing data. 2. Within this part of the code, the predicted values utrainpred and utestpred are incorporated into their respective positions within the train predict plot and test predict plot arrays. These computed values will be utilized for subsequent visualization. 3. The original prices undergo a reverse transformation to revert to their initial values, which are then stored in the original variable. 4. Concatenation of the train predict plot, test predict plot, and original arrays is conducted across the columns to form the predictions array encompassing both the original and predicted values. 5. The predictions array is transformed into a pandas data frame dubbed as result. This data frame is particularly useful for visualization and conducting further in-depth analysis. This code segment proves indispensable for the comparative visualization between the actual prices and the forecasted prices produced by a machine learning model. By amalgamating the original prices with the predicted values, it simplifies the visual assessment of the model's efficacy in predicting prices accurately. This snippet of code is designed to produce a visual representation showing the forecasted and actual values of a collection of stock prices. Here's a breakdown of what the code accomplishes. 1. It kicks off by importing the essential libraries, namely Plotly Express and Plotly Graph objects. 2. It establishes a fresh canvas for the visualization. 3. 3 distinct scatter plots are added to the canvas to indicate the training predictions, test predictions, and actual values. 4. The plot's layout is fine-tuned to enhance its aesthetic appeal. adjusting properties like axis settings, grid lane visibility, and switching to a sleek dark color palette. 5. Annotations, such as the title Amazon stock prediction in a specific font and color, or integrated into the plot. 6. As a final touch, the interactive plot is presented via Fig. Show. This code is valuable for producing engaging and dynamic data visualizations that aid in scrutinizing and understanding stock price forecasts and actual outcomes. Leveraging the estimation capabilities of Plotly empowers us to craft compelling and enlightening plots that effectively communicate data insights. The provided code snippet serves the purpose of extracting particular column information from a data frame labeled data. It singles out the closed column within the data frame and then assigns this data to a fresh variable named pre-Google. Following this assignment, the info function is executed on the newly created pre-Google variable to generate a digest of the data frame's details, encompassing details like data types and non-empty values related to the closed column. This code snippet proves to be valuable when the objective is to extract precise data from a vast dataset for in-depth scrutiny or subsequent procedures. By singling out solely the closed column or specific columns of importance, one can center their attention on pertinent data points and carry out analyses or computations on that specific subset. The info function plays a crucial role in presenting vital insights about the data, ranging from data types to the presence of absent values, thereby playing a pivotal role in the process of data refinement and analysis. In this snippet, the code employs the min-max scaler class from the sklearn preprocessing module to apply a min-max scaling technique to close values of a dataset, likely representing past stock prices of Google. Min-max scaling is a popular method that adjusts data to a predefined range, often between 0 and 1, or in this instance, spanning from 1 to 1. The algorithm for min-max scaling is calculated as ktexiled frax ktexmix texmax ktexmin times texmax texmin texmin in this context 1. A min-max scalar instance is created with the specified range of 1 to 1 using the feature range parameter. 2. The code extracts and reshapes the closed column from the pre-Google data frame into a 2D array via values, reshape 1, 1, 3. The fit transform method of the min-max scalar is utilized to both adapt the scalar to the data and convert the closed values to the targeted range of 1. 1. The normalization of data through min-max scaling proves advantageous for training machine learning models, especially when dealing with features of varying scales. It guarantees that all features hold equal weight in the analysis, which is crucial for algorithms reliant on distance metrics, gradient-based optimization, or assumptions of normal distribution in the data. In this code snippet, the dataset with historical price information for Google stock is divided into input and output sequences to train a machine learning model. The split data function segments the original price data into sequences with a specified length called lookback. Subsequently, the cotrain and utrain arrays are generated to house the input and output sequences for model training, while the ctest and utest arrays are crafted for testing the model. Examining the shapes of these arrays cotrain, utrain, ctest, utest reveals the sample quantity and sequence length in each set. This examination aids in confirming the correctness of the data division and ensures that the model is trained on the right input-output pairs. Creating such sequences prior to inputting data into a machine learning model, like a recurrent neural network RNN or long short-term memory LSTM model, is crucial. These models demand data in a specific structure, usually as fixed-length sequences. The code's function is to prepare the data in a format that aligns with the requirements of training and testing these sequence-oriented models effectively. This snippet of code transforms NumPy arrays, specifically cotrain, ctest, utrain, and ytest into PyTorch tensors. PyTorch stands out as a favored open-source library in the realm of deep learning. The process involves using the torch from NumPy function to switch the NumPy arrays into PyTorch tensor entities. Employing the PyTorch tensor method guarantees that the resulting tensors possess the standardized data type anticipated by PyTorch operations. The conversion of data from NumPy arrays to PyTorch tensors proves crucial when engaging with neural networks in PyTorch. The framework equips users with a broad array of tools and functionalities tailored for working with tensors fine-tuned for deep learning calculations. By transitioning the data into PyTorch tensors, you unlock the potential to harness PyTorch's GPU acceleration, automatic differentiation, and an array of other capabilities that streamline the process of constructing and training neural networks proficiently. The following code snippet is essential for configuring a neural network model, establishing the loss function, and setting up the optimizer for the model while it undergoes training. To kick things off, the GRUI model-gated recurrent unit receives parameters such as input dimension, hidden dimension, output dimension, and the number of layers as its starting point. Next up, the mean squared error mass loss function enters the scene. Utilizing torch, nen, and loss. This particular loss function proves its worth by finding the mean of the squared discrepancies between the model's predictions and the actual target values, making it a go-to choice for regression challenges. Moving along, the Atom optimizer shows up. Sporting a learning rate of 0.1, Atom stands out as a crowd favorite among optimization techniques, dynamically adjusting the learning rate for each parameter throughout training. This adaptability often translates to quicker convergence and enhanced performance. By employing this code snippet, we lay down the foundations required for training a neural network model, outlining the model's architecture GRUI, specifying the loss functions loss, and configuring the optimizer Atom. This framework serves as the backbone for model training on a dataset, ultimately striving to minimize the designated loss function and tweak the model's parameters using the optimizer in response to the calculated gradients. The provided code snippet outlines a standard training cycle for a neural network model utilizing PTorch. Let's delve into the breakdown of each phase to commence. The code commences by initializing a NumPy array named just to log loss values across epochs, setting the starting time, and preparing an empty list GRUI for potential data storage during training. Subsequently, it proceeds to iterate through a set number of epochs num epochs a, generating predictions uTrainPred on the training dataset trained through the neural network model. B. Evaluating the loss between predicted outputs and actual values uTrain GRUI with a designated loss function criterion. C. Showcasing the ongoing epoch count along with the mean squared error mass loss output. D. Recording the current epoch's loss value in the gist array. I. Resetting the model optimizer's gradients. F. Initiating backpropagation via loss backward for gradient computation. G. Updating the model weights by invoking optimizer. Step on the optimizer. Lastly, it computes the overall training duration by deducting the start time from the current time and displays the training time. This code snippet plays a pivotal role since training a neural network accentuates the gradual adjustment of the model's parameters to minimize the loss function. Through successive forward and backward passes in each epoch, the model imbibes insights from the data, refining its weights for improved prognostications. This training loop emerges as a cornerstone in refining the model for its designated task and dataset. In this code snippet, we are utilizing the Sailor object to revert the predicted and original values back to their initial form. To begin with, we utilize the Sailor's inverse transform function to reverse the scaling applied to the predicted values uTrainPred and the original values uTrain GRUI. This step is a standard practice when working with machine learning models, especially those that utilize Sailors like min-max Sailor or standard Sailor to standardize the data during preprocessing. Next, the detach NumPy methods come into play to convert the PTorch tensors uTrainPred and uTrain GRUI into NumPy arrays before initiating the inverse transformation. This conversion process is essential to ensure compatibility with the Sailor object. Once the inverse transformation is complete, the outcomes are structured into data frames labeled as predict and original. This formatting allows for further analysis or visualization of the results. Implementing this code segment is crucial to guarantee that both predicted and original values are on the same scale, enabling more meaningful and interpretable comparisons and assessments of the model's performance. In this code snippet, the Seaborn library is utilized to apply a dark grid style to the plots. It proceeds to establish a figure structure containing two subplots organized in a crow-column format. On the left subplot, a line plot is created using SINS line plot for both the original and predicted data. Alongside, it assigns a title, x-axis label, y-axis label, and conceals the q-axis tick labels. This enables a direct comparison between the original and predicted data on a shared graph. Moving to the right subplot, a line plot of the training loss values, stored in the gist variable, is generated. Once again, titles, x-axis label, and y-axis label are added to enhance readability. to enhance visual appeal and readability. The functions fig, set phi86 and fig, set figwidth16 are used to adjust the figure size. The purpose of this code is crucial for visualizing and contrasting stock price data, predictions, and training loss values throughout the model training phase. Visual representation plays a pivotal role in identifying trends, patterns, and discrepancies within the data, consequently facilitating informed decision-making for refining or validating the model. The provided script is designed to assess the root mean squared errors resulting from a model's predictions on training and test data, reflecting how well the model performs, beginning with generating predictions from the model on the test data. The script then scales these values back to their original form using the provided scalar, facilitating precise ERMS computations. Subsequently, utilizing scikit-learn's mean squared error function, the code determines the ERMS for both the training and test datasets. ERMS quantifies the disparities between predicted and actual values, offering insight into the model's efficacy. Following the ERMS computation for the training and test datasets, the script displays the respective scores. Moreover, the ERMS values for both sets, alongside the training duration, are added to the GRUI list for reference. This code's primary utility lies in assessing the regression model's performance, gauging its predictive accuracy within the training and test datasets. A lower ERMS value indicates superior model performance. Such evaluations aid in comprehending how effectively the model generalizes to novel, unobserved data instances. The provided code appears to be linked to a machine learning algorithm designed to forecast stock prices accurately. Here's a breakdown of its functionality and significance to start. The train predict plot and test predict plot functions are established to generate placeholders mirroring the shape of the pre-sequential array, initially filled with NaN values. Subsequently, the model's projected values utrain pred and utest pred are slotted into the respective train predict plot and test predict plot arrays. These forecasted values are instrumental in plotting anticipated stock prices for both training and test datasets. Following that, the original stock prices are restored to their primary state from the scaled format, employing the scalar to enable a comparison against the projected values. The model's predictions, real prices, and placeholders are fused to craft a fresh data frame named result. This data frame is likely intended for visual representations or in-depth scrutiny of the model's forecasts versus the factual stock prices. In essence, this code plays a pivotal role in illustrating the model's performance in predicting stock prices by juxtaposing the forecasted values with the authentic stock prices. It aids in assessing the precision and efficacy of the model. The following script utilizes the Plotly library to craft a detailed visualization of stock information pertaining to Google. First off, it initializes a new plot by employing Go figure. Subsequently, the script inserts 3 distinct traces into the plot, each representing variant data sets: train prediction, test prediction, and actual value, depicted as line graphs. The subsequent step involves enhancing the layout of the plot by adjusting the x-axis and y-axis, introducing titles, and refining other stylistic aspects to give the visualization a darker theme. The template is set to Plotly Dark. Further enrichment is made as an annotation is integrated into the plot, furnishing essential details about the showcase data, such as Google stock result. To conclude, the plot is showcased via fig show. This script proves invaluable for effectively visualizing and dissecting stock details. Plotly's interactive and visually pleasing plots facilitate the comprehension of intricate data patterns and correlations. The wide array of customization tools within Plotly enables meticulous management over the plot's aesthetics, aiding in the communication of pivotal findings inferred from the data. Below is a script that initializes a new variable called upreasoned. This variable houses a data frame that includes solely the closed column from the primary data frame named dataTims. Subsequently, the info function is employed on the upreasoned data frame to exhibit details regarding its data type and memory allocation. This snippet is crucial for singling out and dealing with particular columns within an extensive dataset. By sieving out redundant columns, the dataset becomes more wieldy, facilitating simplified handling of subsequent data analysis tasks on the specified subset of the dataset. The deployment of the info function imparts valuable insights into the attributes of the isolated data, encompassing details like data types of each column, count of non-null values, and memory usage. Such information proves instrumental in effectively grasping and manipulating the data. This portion of the code is from a data processing task that involves min-max scaling. This technique is commonly used to standardize data within a customized range. The steps carried out by the code are as follows. 1. The min-max scalar class is imported from the scikit-learn library. 2. An instance of min-max scalar is established with a feature range set as 1. 1. 3. A specific column clause is extracted from the presim dataset. 4. The chosen column is reshaped into a tut array. 5. By employing the fit transform method, the scalar is fitted to the reshaped column, adjusting the values to fall within the designated feature range. 1. Utilizing min-max scaling code of this nature is essential for standardizing data within a specified scope. This process enhances the efficacy and reliability of machine learning models, particularly those that are sensitive to data scale, such as gradient descent-based algorithms e.g. neural networks. Standardizing the data aids in preventing particular features from disproportionately influencing the model training solely due to their scale. In this code snippet, the dataset presim is being divided into input sequences train, test, and output sequences train, test to prepare for training and testing a machine learning model. Setting the variable lookback to 20 determines the length of sequences for each input-output pair. The split data function is invoked with the presim dataset and the specified sequence length lookback. This function processes the data, creating the necessary input train, test, and output train. A test sequence is crucial for training a machine learning model. These sequences are particularly vital for tasks like time series forecasting or sequence classification. The displayed statements reveal the shapes of the resultant data arrays train, test, to confirm the accurate splitting and formatting of data for model training and testing. It is essential to validate the correct structure of the data before introducing it to a machine learning algorithm for training and assessment. The presented code snippet demonstrates the process of converting NumPy arrays into PTorch tensors. PTorch, a well-known deep learning framework, relies on tensors as the primary data structure for managing and processing data. In essence, the code accomplishes the following tasks. 1. It brings in the torch library, a pivotal component of PTorch, alongside the torch NN module, which caters to neural network functionalities. 2. The conversion of NumPy arrays, specifically train, test, test into PTorch tensors, occurs through the utilization of the torch from NumPy function. 3. By including the PTorch tensor section, the resulting PTorch tensors are assigned the data type torch tensor, thus ensuring uniformity in data types throughout. The significance of transitioning data from NumPy arrays to PTorch tensors stems from the smooth compatibility between PTorch operations, neural network modules, and tensors. This conversion streamlines various tasks such as neural network training, gradient computations, and leveraging GPU acceleration. This piece of code sets up a group of variables typically employed in the realm of neural networks or deep learning models. Here's a breakdown of the significance of each variable. Input dim. It signifies the dimensionality of the input data, where it is currently designated as 1, denoting one-dimensional input data. Hidden dim. This variable denotes the quantity of units or neurons in every hidden layer of the neural network. At present, it is configured to 32 num layers. This variable specifies the quantity of hidden layers within the neural network, currently established at 2. Output dim. It signifies the dimensionality of the output data, being set at 1, denoting one-dimensional output data. Num-pos. This variable designates the number of epochs or cycles over the dataset throughout the training phase of the neural network. These variables are customarily utilized in the setup and training of neural network models. The specific values assigned to these variables can be customized to suit the demands of the specific problem at hand, the intricacy of the data, and the computational resources accessible. By establishing these variables at the outset, it presents a convenient method to monitor the crucial parameters employed in the neural network model. The provided code excerpt establishes a neural network model utilizing the gated recurrent unit GRUI design with a specified number of layers. It also sets up a mean squared error loss function class and an atom optimizer featuring a 0.1 learning rate to facilitate model training. A GRUI model. The GRUI neural network model is prepared with set input dimension, hidden dimension, output dimension, and layer count. GRUI represents a recurrent neural network RNN layout commonly employed for processing sequential data. MSCLOS, employing the mean squared error loss function, allows for the computation of the average squared variance between modal predicted outputs and the genuine target values during training. Atom optimizer. The atom optimizer serves the purpose of adjusting the model parameters by considering gradients of the loss function concerning those parameters. This optimizer utilizes adaptive learning rates for enhanced parameter-specific training advancement. By utilizing this script, you're able to configure the neural network model for a specific task, establish the loss function for error computation during training, and prepare the optimizer to efficiently update model parameters. Tailoring the model architecture, loss function, and optimizer configurations enables effective training of the neural network to recognize patterns and generate predictions on novel data. The presented code snippet outlines a training loop designed for a neural network model by leveraging a specified model, criterion, and optimizer. Here's a breakdown to grasp the operations performed to begin with. A NumPy array named chist gets initialized for storing loss values across various epochs, along with setting up a timer using the function time to gauge the training duration effectively. Subsequently, it proceeds to iterate over a range encapsulating numepochs, symbolizing individual training epochs within the loop. During each iteration, it conducts predictions utrain on the training dataset HTrain employing the neural network model referred to as model. Then, it proceeds to compute the loss between the predicted outcomes and the actual values utrain GRUI utilizing a specified criterion like mean squared error or MES. The loop also showcases the epoch number and corresponding MES loss value, facilitating the real-time monitoring of training advancement. Furthermore, the loss value is stored in the chist array for seamless tracking of the training evolution. The loop expertly clears out the gradients to prevent carrycover from previous iterations, computes the gradients concerning the model parameters, and updates said parameters leveraging the optimizer referred to as optimizer. A crucial aspect involves calculating the cumulative training time by deducting the start time from the current time post-iterating through all epochs. This training loop underscores its significance in training neural network models by iteratively refining model parameters to curtail the loss function and boost the model's efficacy on the training dataset. By actively monitoring loss values and training duration, we can adeptly oversee the training trajectory and implement enhancements to nurture the model's learning curve and convergence efficiently. This code snippet reverses the scaling transformation applied to two sets of data that were previously scaled. It leverages a scalar object to revert the scaling transformation on the predicted data, eTrainPred, and the original data, uTrainGRUI. Implementing this code is crucial for bringing back the scaled data to its initial scale. In the realm of machine learning, it is customary to process, transform, and scale data before making predictions. However, after generating predictions, it is essential to reverse these transformations to ensure the interpretability and comparability of the results with the original data. This code guarantees that the predicted and original data points can be effectively compared and analyzed. This piece of code leverages the Seaborn library to craft a visual depiction of data. Here's a breakdown of its functionality. 1. It configures the plot style to dark grid via Seaborn. 2. It initializes a figure for the plots and fine-tunes the layout between subplots. 3. It establishes a subplot showcasing two plots side by side. 4. Within the first subplot on the left, it generates two line plots using Seaborn's linplot function for both the original and predicted data. It designates the title a label, I-label, and conceals the axis tick labels. 5. Inside the second subplot on the right, it renders a line plot utilizing Seaborn's linplot function for the training loss data. It specifies the label, I-label, and title for the plot. 6. It enhances the figure's dimensions. This code proves valuable for visually illustrating diverse data sets such as stock prices and training loss. Employing Seaborn to construct the plots enables effortless customization and the creation of visually appealing graphics without extensive, intricate coding. It facilitates enhanced data analysis and comprehension by presenting information visually. This particular code snippet forms a crucial part of the machine learning model evaluation process. Let's break down its functionality. Firstly, it computes the model predictions UTestPred based on the input data HTest. Subsequently, it reverses the transformations applied to the predicted values you train pred and you test pred using a sailor. This step aims to restore the original scaling of the target variable, ensuring the predictions align with the initial data. Next, it applies the same sailor used for predictions to revert the transformations on the actual target values you train and you test. It then proceeds to determine the root mean squared errors between the genuine target values and the predicted ones for both the training and testing sets. ARMS serves as a widely acknowledged metric in assessing regression models, shedding light on the disparities between the predicted and actual values. The code then displays the ARMS values for both training and testing datasets, offering insights into the model's performance. Additionally, it appends the computed training and testing scores along with the training duration to a list named GRUI, ostensibly for monitoring the model's performance metrics. This code snippet plays a pivotal role in evaluating the effectiveness of a regression model. By gauging and contrasting the ARMS values across training and testing datasets, we gain a grasp of the model's ability to generalize to fresh, unseen data. This assessment is paramount in gauging the model's efficacy and pinpointing potential instances of underfitting or overfittings. The ARMS metric aids in quantifying the model's predictive errors, offering crucial insights for enhancing the model and further refining its performance. The given script pertains to a machine learning model, possibly geared towards time series forecasting. Here's a breakdown of its functionality. 1. Initial setup involves creating train predict plot and test predict plot as empty arrays mirroring the shape of the presim array. They are then populated with non-values via slicing operations. 2. The train pred forecasts are integrated into train predict plot, commencing from the lookback index. 3. Following suit, the test pred forecasts are incorporated into test predict plot, with the insertion initiating at plenty train pred lookback 1 for proper alignment. 4. Actual closing prices of item stock extracted from the close column of the presim data frame undergo retrieval and subsequent inverse transformation utilizing a sailor. 5. Concatenation of train predict plot, test predict plot, and original price values transpires to yield a consolidated predictions array. 6. The predictions array transitions into a data frame titled result. This script facilitates the visualization and comparison of model predictions on both training and test data against the factual values. Through visualizations or analyses of the result data frame, users can gauge the model's efficacy and precision in forecasting item stock prices. This snippet of code demonstrates how to generate a visual representation of data using the Plotly library in Python. Let's break down what it accomplishes. 1. Initially, it imports essential modules from Plotly for crafting interactive plots. 2. It establishes a figure object that serves as a canvas to which we can incorporate various traces, such as scatter plots or lines. 3. By employing the CAD trace method, it integrates traces into the figure. This entails specifying the plot type like a scatter plot, the data for the x and y axes, the plot mode, and a distinctive name for the trace. 4. It adjusts the figure's layout to tailor the plot's appearance, encompassing properties of the x-axis and y-axis, legends, and the chosen template, a dark theme in this case. 5. Annotations are introduced to furnish supplementary details such as the plot's title. 6. Lastly, the plot is exhibited using fig show. This code proves beneficial for visualizing and scrutinizing time series data, contrasting different datasets, and facilitating data-driven decision-making rooted in insights derived from the generated plots. The interactive functionality of the plot encourages exploration and enhances comprehension of the data. The presented snippet of code retrieves the close prices from the data Microsoft data frame and stores them in a new variable named pre-Microsoft. Subsequently, the info method is employed to exhibit details concerning the pre-Microsoft data frame, encompassing column data types and memory usage. This code serves to validate the organization of the extracted data, ensuring its alignment with anticipated standards prior to engaging in further scrutiny or computations. It aids in comprehending the varied column data types, which are essential for precise analyses or visual representations. In essence, this code facilitates data examination and preps it for ensuing procedures without divulging all dataset particulars. In this code snippet, the close prices of Microsoft stock are being scaled using the min-max scalar class from the scikit-learn library. To break it down, 1. the min-max-salar function adjusts the data to fit within a defined range. Set here as 1, 1, 2. Initially, the close prices of Microsoft stock get isolated and reshaped into a 2 array since min-max-salar necessitates a 2 input. 3. Following that, the salar gets calibrated to the close prices data through the fit transform method, aligning the salar with the data and simultaneously adjusting the data within the specified range. 4. Ultimately, the resettled close prices are reassigned to the close column within the pre-Microsoft data frame. This code serves to normalize or standardize numerical data within a specific range here. 1. Such scaling practices are key in the realms of machine learning and data preparation to ensure that all elements hold equal weight in the model, averting any single feature from overshadowing others. Standardizing the data can also enhance the efficacy and optimization of machine learning models. The provided code segment seems to be related to a project involving machine learning or time series analysis with historical stock price data from Microsoft. Here's an overview of what the code accomplishes. 1. By setting lookback 20, the model is designed to examine the preceding 20 data points to forecast the subsequent data point. 2. The split data pre-Microsoft lookback function is invoked to split the historical price data of Microsoft pre-Microsoft into sequences for input and output values for training and testing purposes. This function likely generates sequences of length lookback from the historical dataset. 3. The outcomes obtained from the split data function are assigned to train input sequences for training, train corresponding output values for training, test input sequences for testing, and test corresponding output values for testing. 4. The subsequent print statements reveal the dimensions of the arrays containing training and testing data. This step is crucial for confirming the data dimensions align before initiating the machine learning model. In essence, this code readies the data for a machine learning model by constructing input-output pairs from historical stock price information. It's vital to partition the data into training and testing subsets to effectively train the model and assess its performance. The inclusion of a lookback window enables the model to discern historical patterns, aiding in forecasting future data points. The provided code excerpt demonstrates the utilization of the PTorch library to transform NumPy arrays train, train into PTorch tensors, which are specialized multi-dimensional matrices ideal for executing deep learning tasks on Jupyter. To convert NumPy arrays to PTorch tensors, the code employs the torch from NumPy function. Additionally, it employs the PTorch tensor method to explicitly designate the data type of the PTorch tensor as torch tensor. This specific step is essential to ensure proper formatting and compatibility with various PTorch operations. The conversion of data from NumPy arrays to PTorch tensors plays a fundamental role in constructing neural networks with PTorch, facilitating smooth integration with the platform's tensor-based functions and offering GPU acceleration for computations. This coding segment guarantees the data is appropriately structured for subsequent processing using PTorch's deep learning functionalities. Below is an overview of the numeric values assigned to various variables in a code snippet. First off, we have input dim, which establishes the quantity of input features for a neural network model. Here it is designated as 1. Next up is hidden dim, indicating the number of neurons in each hidden layer of the neural network. For this scenario, hidden dim is fixed at 32. Then there's num layers, which dictates the total count of hidden layers within the neural network. In this instance, num layers is initialized to 2, signifying the presence of 2 hidden layers. Moving on to output dim, this variable determines the quantity of output units in the neural network model. Here, output dim is set at 1. Lastly, we encounter num epochs, setting the number of training epochs or iterations for the neural network. It is established as 105, indicating that the model will undergo training for 105 epochs. These variables play a pivotal role as foundational parameters essential for setting up and training a neural network model. By presetting these variables, developers can seamlessly tweak the network structure, input dimensions, and training configurations to align with the specific problem or dataset at hand. In this snippet, a neural network model is being constructed in PTorch using a gated recurrent unit GRUI configuration. The model is being established with defined input dimensions, hidden dimensions, output dimensions, and the number of layers. The GRUI functions as a type of recurrent neural network adept at grasping dependencies in sequential data. The utilization of this class facilitates the computation of the mean squared error between the model's output and the target values. The ATOM optimizer is employed to iterate the model parameters by leveraging the calculated gradients during backpropagation. Utilizing the ATOM optimization method with a learning rate of 0.1, this segment is crucial for setting out the neural network structure, specifying the loss function for training, and configuring the optimizer to adjust the model parameters for reducing the loss throughout the training phase. These elements play a vital role in efficiently training a neural network model on a specified dataset. Within the training loop of a neural network model, this code segment serves several key functions to begin. It creates an array called chest with a length set to numpose to hold the loss values for each epoch. Following this, a timer is initiated to gauge the duration of the training process. The code then proceeds to iterate through a range spanning numpose, conducting the following actions for every epoch: generating predictions utrain based on input data train and the model, computing the loss by comparing the predicted utrain to the actual values utrain GRUI using a specified criterion, displaying the epoch number along with the mean squared error mace loss, saving the loss value in the chest array for loss tracking across epochs, initiating backpropagation by invoking loss backward for gradient computation, adjusting the model parameters via the optimizer with optimizer. Step: upon concluding all epochs, the total training time is calculated and printed. This code block assumes a critical role in the training of a neural network model by repeatedly traversing the training data, evaluating loss, and refining the model weights to minimize loss via optimization techniques. The training loop facilitates gradual model enhancement until reaching a satisfactory performance level on the training data, ensuring the model's adequacy is steadily improving. Notably, the code snippet monitors training progress by reporting loss at each epoch and monitors the training duration to assess training efficiency. This snippet of code appears to be a component of a machine learning or deep learning model involving neural networks like a gated recurrent unit GRUI. It is designed to carry out predictions and subsequently reverse the outcomes to their initial scale. The process involves utilizing the scalar inverse transform function to revert the predicted results and actual labels to their original scale. This step is commonly practiced when the data underwent preprocessing and scaling prior to model training. The tensors, namely utrain and utrain GRUI, hold the forecasted values and true data points. To facilitate the reverse transformation, detach numpy is employed to retrieve the values as numpy arrays from these tensors. Subsequently, the adjusted forecasted and initial values are saved in pandas data frames for convenient visualization and potential further scrutiny. The inclusion of this code is crucial in scenarios where the input data was subjected to scaling or transformation before model training. It enables making predictions in the scaled domain, followed by reversion to the original scale for analysis and interpretation. This approach guarantees that the predictions are understandable and comparable to the initial dataset. In this snippet of code, a figure is created with two subplots. The first subplot illustrates the original data and predicted stock prices through line plots, setting titles, axis labels, and styles with Seaborn. The second subplot displays the loss values throughout training epochs with a line plot, also customizing titles, axis labels, and styles using Seaborn. By employing Seaborn to apply the dark grid visualization style, the plots adopt a darker background color with grid lines. This adjustment enhances the visual appeal and clarity of the plots, aiding in data interpretation and drawing attention to the presented information effectively. Maintaining a consistent visualization style across plots is key to improving the overall aesthetics of data representation. It plays a vital role in ensuring that the plots are visually engaging and easily understandable, facilitating effective data analysis and communication. Assessing a model's performance is a fundamental task in data analysis. The code under review gauges this by calculating the root mean squared errors for the model on both training and testing datasets. Here's a breakdown of the process to start. The code predicts values for the testing set using the model designated as model and the input testing data test. Next, it normalizes both the predictions and the actual targets for both the training and testing sets back to their original scale utilizing the scalar inverse transform function. The RMS is then computed for the training portion utrainpred and utrain and the testing portion utestpred and utest with the assistance of the mean squared error function from Sclern. Metrics. By taking the square root of the mean squared error for the training and testing data, the RMS values are derived. Following this computation, the code prints out the training and testing scores RMS to the console. Lastly, the training score, testing score, and training time values are appended to a designated list named GRUI. This code holds significance as evaluating the effectiveness of a model is vital for gauging its data fitting capabilities and for making comparisons between different models or configurations. RMS, a widely used metric for assessing regression models, offers insight into the model's precision in predicting continuous values. The transformation of scaling is deemed essential when handling normalized or standardized data to ensure accurate interpretation of errors within the original data framework. The provided code snippet pertains to utilizing a machine learning model for time series forecasting. Its functionality can be elaborated as follows to start: 2 arrays, train predict plot and test predict plot, or set up with the same shape as the pre-Microsoft dataset, initially containing non-values. These arrays are designated to hold the forecasted values for the training and testing sets. Accordingly, subsequently, the model's predictions for both the training set utrainpred and testing set utestpred are slotted into the appropriate positions within train predict plot and test predict plot. Following this, the original prices are re-established as original by reversing the scaling transformation executed during preprocessing. This step is crucial for juxtaposing the predicted values against the genuine ones accurately. Next, the anticipated values for the training set, testing set, and original data are consolidated into a unified array named predictions, including nonnies as markers for the missing values within the sequences. Ultimately, these predictions are amalgamated into a data frame termed result, facilitating their utilization for visualization, examination, or further scrutiny. This coding approach aims to streamline the organization and graphical representation of predictions in conjunction with actual values, fostering enhanced visual analysis and comparison. This visual aid plays a pivotal role in evaluating the model's efficacy and aids in making well-informed decisions based on the forecasted outcomes. The following script employs the Plotly library to craft a graphical representation illustrating data pertinent to forecasting Microsoft stock trends. It initiates by establishing a figure and subsequently inserts 3 scatter traces depicting the train prediction, test prediction, and factual stock values across a specified time frame. Moreover, the script tailors the plot layout by personalizing the X and Y axis settings and implementing a dark theme template for a polished appearance. Utilizing annotations, it appends a title to the graph bearing the text Microsoft stock prediction. Ultimately, the interactive Plotly figure is showcased, providing a dynamic platform to explore and engage with the stock forecast data. Leveraging this script facilitates the generation of lucid and captivating visualizations crucial in deciphering and evaluating stock prediction outcomes effectively. The array of customization features afforded by Plotly elevates the legibility and overall visual appeal of the plot.